Hello, and welcome to the third in this three-part series of tech exchange talks titled The Move into Millimeter Wave Frequencies. Today I'm speaking with Giorgia Zucchelli. Giorgia is product manager for RF and mixed signal at MathWorks, and we're going to talk about how engineers can adapt to this changing design environment. And welcome back, Giorgia.
Thanks, David.
Good to have you. In the previous two parts of the series, we talked about in the first part, interfering signals and equalization algorithms, as well as system interoperability versus bandwidth. Part two, we delved into requirements and challenges of millimeter wave systems, including antenna array design and dealing with things like grading lobes and beamforming algorithms. And today in part three, we'll dig into the challenges of analyzing these systems, and we'll cover some design and implementation issues. We'll talk about assessing model fidelity and other complex aspects of system simulation. So let's start with talking about approaches for analyzing these complex systems. Like, say, for example, a system with 1,000 antenna elements. What are the typical challenges that designers would face in getting something like this up and running?
Yeah, great question, and very, very actual, very contemporary, given that we are really moving towards massive MIMO, even ultra massive MIMO. I recently heard this term to really represent arrays that are covering entire facades of buildings. So 1,000 antenna elements is really what we are working on today, and it might be on the low side in the future. There are challenges on multiple levels, I believe, in the implementation of the systems. Challenging at the implementation level, really, like trading off the power of that the system requires, the area, the real estate. This has impact, for example, in the choice of the array configuration itself. Do we use arrays? Do we use subarrays? How do you divide essentially the network, for example, to take into account amplifiers, power amplifiers? How do you feed the network? How does it warm up? What's the heating constraints? Is one of the larger constraints when developing such large arrays. And also, how do you perform beamforming? Is it digital? Is it analog? Is it hybrid? The design problems from a technology and the signal processing perspective are so tightly connected that the two aspects cannot really be separated. And everything that is an implementation challenge also reflects directly on the design and analysis challenge, on the computational complexity. So you have 1,000 antenna elements. Can you simulate them? Can you analyze them using electromagnetic solvers? And can you simulate them together with the RF front ends, together with the equalizer in terms of digital signal processing, in terms of maybe with the linearization algorithm, together with the data converters, the ADCs and the DACs. So there are challenges really on the implementation and on the design phase. And just to add to this, with 1,000 of antenna elements, it's great because you can really build antenna arrays with a very focused beam, really narrow beams, which is great because it makes it much more robust to interferers, like we were discussing last time. But it also makes them more sensitive to errors in the array configuration, literally the physical position of the antenna elements in the array. And to errors in the pointing angle, essentially, where are we directing the array? So with that respect, it becomes almost a must or compulsory to do the array analysis and simulation together with the digital signal processing algorithm to see if we can effectively correct these errors. So it's a hard problem both on the design side and on the analysis, on the simulation, and on the implementation side, I would say.
So how would one go about modeling such a system, Giorgia? And how do you assess the fidelity of the models that you're using?
I think somebody said that there is no perfect model, in the sense that every model has some finite level of fidelity. By definition, is a model is a model. So when you have to model and simulate and analyze arrays that have so many elements, sure, you can do it brute force, but that's very, very, very expensive. Very expensive from a resource perspective and very expensive from a timing perspective. Even if you have a very large machine with lots of cores and lots of memory, not all problems are by nature parallelizable. In particular, if you think about a large antenna array, you might think like I can parallelize the signals feeding to each antenna and process them in parallel. But at some point in time, the data has to come together. And even when you parallelize simulations or an analysis, at some point in time, the data has to come together. So there is always an overhead in distributing the parallel data and then gathering it back. So yeah, brute force can help. But the bottom line is no matter how much brute force you're going to use, you will also need to raise the abstraction level. So modeling the system at a higher level of abstraction is highly recommended for a number of reasons. First of all, because speed of developing a model and speed of feedback that the model can give you helps you in iterating more rapidly. So with that respect, raising the abstraction level allows you to do maybe a first pass of the design that is faster and gives you information from a design perspective more rapidly that you can use later or in your the refinement of the design. And then, of course, after that, you can also go to brute force and scale up the simulation to hundreds of cores if you have accessibility. So raising the abstraction level, what does it mean? Sounds good on paper, but what is the practical consequence? It can be different things. For example, for an antenna array, you might think of using the infinite array approach. So if I have a very, very large array with thousands of antenna elements, rather than performing a full wave electromagnetic analysis of the structure as it is, you can consider just one element and consider it to be embedded into a structure that essentially it's an infinitely large lattice, just reproducing itself. There are several techniques in the electromagnetic space that allows you to deal with that, and that provides a much faster performance. Other ways to raise the abstraction level, for example, let's say that you have 3 RF components or 5 RF components in a cascade, like to represent a receiver, just to make an example, like a filter, a noise amplifier, maybe a demodulator, maybe another filter. Something to that extent. One thing that you might consider is model each of the components as they are, or model the cascade of the 5 components or the 4 components as a single equivalent macro behavioral model, let's say. Rather than having 4 components that generate noise, we can say we assume that all the noise is input referred. We create one equivalent noise source that generates the same noise as the entire cascade. It's an approximation, but it's an approximation that in many cases can be acceptable. So this is the type of trade-off that you as a designer or you as a modeler of the system will have to consider. Because like I would say, there is no right and wrong in this way. Everything is an approximation. So it's up to you as a designer to maybe use different models that operate at different abstraction level and say, this model is accurate, I can trust it, I understand it, and then I abstract it away in such a way that, for example, I only have noise generation at the input, or I have only nonlinearity modeled at the output. So that's really how you can go about it. One typical problem that I really like in this context, for example, is with antenna arrays, is assessing the coupling. Where is the coupling occurring? For example, if I have a very large array, do I really need to take into account the coupling in between each and single individual element? Or maybe I can just consider the coupling to the next 2 adjacent elements, left and right, or maybe top and bottom, depending on your array configuration. So those are really the type of considerations that only as a designer you can assess, and that is the trade-off that you have to play and consider. Very nice modeling problem, essentially.
Yes. In previous installments in the series, we've touched on the topic of artificial intelligence. How does, or does it at all, AI fit into complex system modeling of this sort?
Yeah, it's a new tool, AI, or it provides a new family of tools, and it does help in solving problems with a large computational complexity or a large computational cost. For example, starting with probably one of the most traditional examples is if you want to design an antenna array and you want to optimize its performance for a certain bandwidth, frequency, gain, then you have to perform lots and lots of electromagnetic analysis. And electromagnetic analysis is expensive. So where AI can help is in building these surrogate models that help in speeding up the computation of the objective function. So rather than performing an electromagnetic analysis at every step of the optimization, you only perform a few electromagnetic analysis, build a surrogate model that essentially represents a faster model that can be used to compute your objective function. This is one traditional example where AI has helped already practically for many years. Going one step further, some of the things that are happening nowadays is to use AI to build pre-trained networks to really solve antennas. Actually, in Antenna Toolbox and MATLAB, we are shipping now the first objects and examples where you don't have to solve an antenna at all, because we provide a trained AI network that allows you to analyze the antenna without even performing any electromagnetic analysis. And we can do this on the basis on a catalog of antennas. So we know what is the shape of the antennas. We have solved the antennas. We have done the work for you, if you like, on many different data points, and use the data points to train a network. And then we can just use the network for that antenna. That, of course, works for very specific geometries, but it's a starting point, and it's something that will grow in the future as well. Another space where AI really helps is, for example, in beam steering, for example, algorithms. We already talked about digital distortion. Beam steering is another good case because the arrays become very large. Like I was saying before, the beam becomes very narrow. Essentially, the system becomes very sensitive to pointing errors. So reinforcement learning techniques are now starting to be applied for array calibration and correction. So to make sure that, for example, based on the received signal strength, the beam can be pointed more accurately. I always think of reinforcement learning as a sort of engineering method on steroids, trial and error on steroids. And I like it very much because I find it very intuitive. So I think that this is a good emerging area where we will see more and more analog application and RF applications of AI.
Yeah, it's definitely an interesting area that's getting a lot of people's attention for sure. Let me step back to trade-offs. You talked earlier about speeding up analysis by raising the abstraction level. What are some of the other typical trade-offs one might find in this large simulation of large complex systems?
Yeah, everything pretty much is a trade-off, however you look at it. So there are trade-offs on the implementation level. So, for example, you have to trade off a spectral occupation, for example, with power, with computational resources in terms of digital signal processing, and against, for example, the performance. How many users you're gonna serve, what is the latency of your system, what is the range of your system. So there are trade-offs on the implementation side, really on the, for example, how narrow my beam is, how large my array is. Those are two contrasting requirements. On the modeling side, the trade-offs with respect to fidelity and simulation speed or analysis speed are more on the side of how much time or how much resources I have for the simulation, or the performance of the simulation versus the fidelity of the model. For example, do I model every single component, or I model the overall performance? So those are some of the trade-off that you need to consider very carefully. Or going back to the example that I was mentioning before for coupling. I mean, talking at millimeter wave, when the antennas are really small and they're really positioned, packed together close to each other, then you really have to consider, is coupling important, first of all, and what coupling is important? Where do I essentially set the boundaries of my system? So those are some of the trade-offs that you need to consider with analysis. I often like to use I always use models at different level of abstraction exactly for that reason, to assess if is a trade-off is acceptable or not. Always try to simulate the same phenomena or the same aspects with multiple models to gain trust that I'm modeling the right things.
Okay. If an engineer wants to perform multi-carrier circuit envelope simulation, how do you effectively balance model fidelity and speed when you're simulating out-of-band interference?
Yeah, let me step back. Circuit envelope is a great technique, and in itself it's a trade-off. So we can go from transient simulation or real passband simulation, where we pretty much simulate everything from 0 Hertz or DC up to the range of frequencies that you are interested in, plus because of Nyquist, and plus because you always need some oversampling, which means that if you are simulating a system in the gigahertz range, you go from 0 to maybe 100 gigahertz, which means a very, very small simulation time step. And that's in general, it's very accurate, but very time consuming, very expensive. On the opposite side of the spectrum, we have an abstraction that is called equivalent baseband modeling, where essentially you only model the little portion of your spectrum around the signal of interest. And that works fine for most narrowband systems, in the sense that you ignore everything that happens outside the little portion of the spectrum that you're looking at. Circuit envelope is in between, and circuit envelope allows you to adopt the equivalent baseband abstraction, but extend it to multiple bandwidths, hence the multi-carrier circuit envelope simulation. It is actually based on harmonic balance. That is again a technique that has been around for decades now to analyze RF systems. So in this context, the circuit envelope can be almost cover the entire range of abstraction. It can be reduced back to full real passband and real transient by simply setting one carrier frequency with a very large spectrum, or to equivalent baseband, where you have a single carrier frequency but a relatively narrow spectrum without looking at any intermode products. So the circuit envelope trade-off that you as a modeler will have to decide is how many harmonic tones on which you perform the analysis, how many mixing products you're looking at, how many harmonics generated by your nonlinear components you want to analyze, versus what is the bandwidth of the spectrum that I'm looking at, or what is the window that I apply to each of these spectral components. It's a fairly straightforward trade-off, frankly said, because if you have, for example, 3 harmonics, then you perform 3 simulations, and if you double your bandwidth, it's like essentially you reduce your time step by a factor of 2, which means it will take twice as much. So everything is pretty much linear with the number of frequencies, and inversely linear to the bandwidth or the time step. So it's a very powerful technique, and it's fairly straightforward, but it still can be tricky, because then the question becomes, but how many harmonics and what is the bandwidth that I need to perform the simulation? That's really where you as a designer, as a modeler, you need to be aware of.
Okay. So that, linearity being straightforward. What about non-linearity? Um, what are the trade-offs for multi-carrier circuit envelope simulation when you consider higher order even and odd harmonics? And how does that impact the accuracy and the speed of the simulation?
Yeah, exactly. Yeah, that's exactly what I was leading towards. Is It depends on your system, and it depends on your signals. So that's the tricky bit. So if you have, for example, um, let's say you operate with an amplifier that has some saturation, and you send the signal through your amplifier. If your signal is relatively small and doesn't excite the nonlinearity of the amplifier, then you can keep your harmonic order relatively low. And by the way, this is only something that you will know once you run the simulation. If your signal instead as a high power, then it will excite more of the nonlinearity of the power amplifier of your amplifier, and therefore you will need a higher order of nonlinearity. And this becomes a little bit more tricky when you have signals that have a high peak to average power ratio, in the sense that you might have a signal that maybe for 90% of the time is small signal, but for 10% of the time becomes large signal. Now, the good news is that let's say that you have an amplifier, and then you send this 5G signal that is maybe around, I don't know, 5 gigahertz, and then you will have harmonics at 10 gigahertz and 15 gigahertz and 20 gigahertz and 25 and so forth, depending on the power of the signal. Well, the good news is that if you are only interested in what happens at 5 gigahertz, you don't need to push the harmonic order very high, in the sense that you need just to have an harmonic order that is sufficiently, just a little bit larger of what of the harmonic you're interested in. So if you're interested in the first harmonic, maybe an harmonic order of 3 is sufficient to get good quality results. If you're interested in the harmonic order third, then you will have to push it further, maybe to order 7 or order 9. Those are the type of considerations. Sometimes you have systems that operate on higher order harmonics or harmonics essentially, for example, for clock generations, and then you will have to push it higher in terms of order, but that's a type of trade-off that you will have to consider. And yeah, using harmonic balance, understanding how harmonic balance allocates the power through the different harmonics is essentially the fundamental rule of thumb that you need to keep in mind.
All right. How about simulating mixing effects? What are some of the key considerations and challenges when you simulate mixing effects, and including things like reciprocal mixing?
Yeah, similar story, similar but different. In this case, I would say where I would start is a good frequency plan, in the sense that you need to do, and this you can do a lot of analysis here statically when it comes to mixing with mixers with where you might have information such as intermode tables, or reciprocal mixing effects such as anticipating a low leakage or a ref leakage, depending if you are converting up or down. But I would start there from a good frequency plan, that is static analysis of your system, to understand where the, how can I say, the most critical tones or the most critical components might end up being. And once you know that, you can then move into the simulation domain. So first you statically analyze your system, and then you move into the simulation domain. And you verify that your assumptions are indeed valid, and you verify that indeed those are the right harmonics to be considered. There's a good way of working that is, I always try with slightly higher harmonic order, and then I reduce it. And if the results do not change, this is a good news. Then I know that I can cut on the harmonic order, or I can cut on the number of intermode products that I can be interested. But that's a very, like I was saying, it's a very trial and error. It's a very engineering, poor man engineering approach. Starting with a good frequency plan is probably a better a more solid approach for this type of problems, especially when you deal with superhet architectures that have lots of stages going up and down in frequencies.
All right, that'll do it for today. We covered a lot of ground, Giorgia, and that'll wrap up our three-part series on the move into millimeter wave frequencies. And I'd like to thank Giorgia Zucchelli of MathWorks for her insightful presentations on this topic, and invite our audience to look for more Tech Exchange Talk videos coming in the future.